Okay, so Fs has to point this way. Go ahead. Fs has to point this way. It's the only thing that is making sure it's going always towards the center of the circle. So I guess which direction would that be? A, B, C, or D? D, just in the same direction of centripetal acceleration as well. So in the D direction. Okay. Now we start with the actual what? With the actual numerical problem. All right. Yeah, is this you? Okay. A model airplane with a mass of 0.211 kilograms or 211 grams pulls out of a dive. Pulls out of a, by the way, these problems, if anyone here or if you know anyone who's basically doing Air Force, those problems are so freaking important. Why? Because when a pilot falls out of a dive, what does that mean? There's what on them? There's centripetal acceleration, which is very important that their body is capable of what? Of handling it. Otherwise, they could actually what? They could just black out. Why? Because of the force on the what? On the blood in the head. It could be what? It could be drawn either. So it could be drawn from the head, and they like astronauts actually go through this all the time. Whenever they what? So obviously, when you launch a rocket, which way does it launch? Down or up? It launches up. But here's the thing: the acceleration is so huge, but the what? But when you yank, okay, when you're in an elevator and the elevator starts moving, how do you feel right at the beginning? You go like this, and that's just an elevator. Imagine a what? Imagine a rocket trying to accelerate so quickly and so fast to escape Earth gravitational field, basically at a huge, what we call escape velocity, which will we do when we do orbits. What's going to happen to the blood in your head? And that's why astronauts never what? Never get launched into space what? Standing up. You don't want them standing up because if you're standing up and the blood is drawn from your skull, what's going to happen? Gone. That's it. You're basically fainting, right? So what do they actually do? They lie on their what? They lie on their back. So at least what? The blood is only drawn from the what? Yeah, they get temporary blindness. Yep. They get they actually get like a quick blackout because again, there is less blood going to the what? Going to the vessels, going to the capillaries in the eye than right before launch. But then what's going to happen? What's going to happen then? The speed is going to what? Neutralize, or the speed basically is gonna get constant, and then what? No more force is pulling it down. No more force is pulling it down. That's so the bottom of the dive is a circular arc. Perfect. It had to be a part of a circle. Otherwise, we cannot apply any of yesterday's or today's equation. At the bottom of the arc, the plane speed is 21.7. Go ahead, everyone. So you have this diagram, right? Okay. What's the magnitude of the upward lift force that will make sure that the plane actually what starts going up? Okay. Tell me the forces. Definitely. What's the first force on the plane? Go ahead. Gravity. Okay. By the way, can planes ever fly in vacuum? Can birds ever fly in vacuum? How do birds fly? Seriously. I know it's a very basic question, but how do they fly? Yep, Ahmed. Exactly. They flap down. So Newton's third law. They flap on the air. What happens? The air pushes up back, okay, by creating what we call a pressure difference. What's another reason that birds cannot fly in vacuum? Can you exist? Can you exist in vacuum? Question. Why do you, okay? Two questions here, everyone. What happens? How many people flew airplanes before? Like actually flew an airplane. What happens to you as the plane is taken off? What do you keep doing? Anyone? What do you keep doing for the first few minutes after takeoff? How many people keep doing this? Why do you do this? Why do you almost like dislocate your jaw like this? No, seriously, it's bad. When I was in Edmonton, same thing. I'm like, by the way, don't excessively do it. You might actually dislocate your jaw. But why do you do it? What are you trying to accomplish here? Uh-huh. Oh, cabin pressure. Can you explain to us what cabin pressure means? Uh-huh. High in the sky, I like that. Uh-huh. Okay. Question to you. You know that the cabin is pressurized, right? It has to be. Because as you go up, what happens to the atmospheric pressure? Does it go up or go down? Goes down. When some how many people follow like weather reports sometimes? What does it mean? What does wind mean? What's wind? You're there. Wind is what? The motion of air from what front to what front? From high pressure to what? Low pressure. How many people have heard of osmosis? Osmotic pressure. Or how many people did biology here? Osmosis. What's osmosis? By the way, it's the same principle. Exactly. You have a membrane and you have more concentration here than here. So what happens? The region with more concentration gives what? Gives the material to the less concentration. Guess what? Wind is the same thing. You have a high pressure front and you have a what? Low pressure. So wind always goes from where to where? To what? What does anyone know? Does anyone know what's the scientific word when things balance out? Ic. You do it in chemistry. Equilibrium, right? What does equilibrium mean? Things are what? Not changing anymore. Okay? So when you go high in the sky, first of all, you're on the runway. The pressure inside the plane is equal to the what? Pressure outside the plane. You keep going up. Now the cabin is pressurized. But is it perfectly pressurized to the exact same pressure outside on the runway or slightly less? Yeah, they can never perfectly what? Perfectly match the atmospheric pressure right here outside to like 50,000 feet above. So what happens to the pressure inside of the cabin as you go up? It gets what? It gets slightly what? Come on, slightly less than the one we're experiencing right now. So, by the way, is your body a closed system or an open system? Your body. Come on, are you perfectly sealed? You're not. You've got what? You've got basically openings, even your pores in your skin, right? So that means what? You go high in the sky. As you go, so far, what's the pressure inside of your body? It's still what? Still what? One atmospheric pressure, right? One atmospheric pressure. But you're going up. Now, what's happening to the pressure out around you in the cabin? It's slightly what? Less. So where is there more air pressure? Outside your body or inside your body? So okay. So the air is trying to what? Enter in or escape out? It's trying to escape out. But the problem is, and okay, so the air in your head is trying to escape out. So what is it? What is it pressing? What is it pressing on? Your what? What's inside of your ear? Yes, don't use Q-tips way too deep, otherwise you might perforate your eardrum. So what's happening here? It's pushing on your what? You're pushing on your eardrum. That's why you start hearing what like a muffled air stream. And so what you're trying to do is what? What are you trying to do? Open up. There's a channel actually. There's a channel connecting your what? Your larynx to your what? To your ear. So the more you do like this, what are you trying to do? Open it. And once you open it, what do you hear? Ah, the sweet sensation of relaxation, right? Because you hear, you actually sometimes, if the pressure difference is high, you actually hear the air actually what? Escaping. Guess what? Does that happen in reverse again? Yes, when you what? When you land. But now it's the what? It's the reverse because now the air is what? Trying to what? Go in. So what do you do again? You do the jaw again and you open. Does that make sense? That's exactly what happened. So the question now is okay. So what's the other reason that birds can't fly in vacuum? You can't even exist in vacuum because all the air inside of you is gonna what? Is gonna leave your body. But here's the thing: when you're in vacuum, the pressure difference between the air in your body and the air outside your body is so huge, the force pushing on your skin to actually expand it could actually rupture your skin. That's why anyone who goes to space without a pressurized spacesuit dies instantly. They explode. They actually explode. Why? Because the air is ballooning them up to actually what? To just, equalize it. Okay? So the question now is, which way? Okay, is there any tension in this problem? Is this plane connected to a string? No. Um, is there any applied force on it? Is someone physically pulling it up? Not someone, but something. Is there normal force on it? If you say yes, technically you're right. It's not in vacuum, it's in air. Whenever something flies, it's flying on a what? On a pillow of what? In a pillow of? It's like teaching grade school. Idiots, they don't know there are cameras in. I'll talk to the office. What time? 9:09. Nice. Okay, so the only thing that's making sure that this has any chance of being lifted up is what force? What force? We call it normal force if there's a surface, but there is no real surface. So what do you call it? Now we have another name. We call it the what? Yes, this is what's known as what? Lift force. Lift force is basically normal force, but when you fly in what? In absolutely any gas, which usually would be what? Would be air. So now, what do? We put F lift. Never, again, technically it is F normal. Never call it F normal though, because you do not see a surface. But you know there's something acting like a surface, acting like a lifting surface. So go ahead and F. Let's actually call it F lift. Any other forces? Sure. Well, hold on. I'm asking any other forces. Forces. Engineering forces. What's up? What do you want? Okay. It is actually, it's staying in motion. Okay, it's staying in motion because something we're going to cover next week. Energy. Not technically force, energy. Okay? So here's my question now. If those are the only two forces, where is the center of the circle? Can someone point to it? I mean, again, the circle is hypothetical, but we know it exists because it's going in a circular way. Hmm. Exactly. The center of the circle is right here. Everyone, just make a point right here. So that means which way is the centripetal force on the plane? Forget all the other forces on it. The hypothetical centripetal force. Which way does it point? Always towards what? Always towards the center. But I just told you a couple of slides away that you do not put FC on the diagram. But what can you put on the FBD? Yes, you never put force FC, you put AC. So go ahead and just put AC this way. Do you remember? Okay, what was probably the second or third step when we did force problem? We had to choose a what direction? We had to choose a positive direction. In any centripetal force problem, where do you think this positive direction is always going to be? Out of the circle or into the circle? Into the circle. Everyone, from now on, any AC problem you do, once you sketch your AC, go ahead, put a plus here. So now can you tell me which force is pointing positively? Which engineering real force is pointing positively? F left, which one is pointing negatively? Done. That's it. FG. So now we're ready to do the what? Now we can do the math. Okay. So everyone, let's. I think you have a slide for that, right? Yes. Okay. What's the FC formula? Come on. I just taught you a few slides ago. What's the FC formula? So FC equals mv squared over r. But I told you that FC is really nothing but what? What's Newton's second law? No, the first part of Newton's second law. F net. FC is nothing but F net. If you would apply the positive negative idea to F net here, how would you write FC? واضح? Exactly. FC technically is F net, so it's positive F left minus FG equals mv squared over r. Am I now on track to solve this? Yes. What do you do with FG all the time? You make it mg. Great. So F left minus mg equals mv squared over r. Okay. Do I know the mass of the plane? Yeah, it's a small model plane. So what's the mass? Yes, 0.211 kilos. Do I know the radius of the motion? The hypothetical radius of the circle? 25.6 centimeters or meters? meters. Okay, so it's a big circle. And do I know the speed of the plane at that instance? 20, sorry, 21.7 or 2.71? 21.7. Go ahead, plug in. However, maybe before you plug in, what should you move to the other side? Because technically you're only solving for F left. mg, there you go. And then, could you simplify your life by taking m as a common factor? By the way, can you cancel m? What would you say to someone who says, oh, factoring is canceling? They are the same thing. Is factoring and canceling always the same thing? Are they sometimes? Only in one case. If your common factor is common where? Everywhere. You got it. Is there an m with f left? If there were, be my guest. Slash, slash, slash. But you can't cancel, but at least you can factor. And I'm not saying you should factor. I'm just telling you, if you want to do it, you can go ahead. So f left equals mg plus mv squared over r. And now we can just plug in. M is 0.211 times a 9.8 plus, yes, go ahead. Oh, no, I didn't say you can't factor it. I said you can't cancel it. Oftentimes, even sometimes in first year, I see people just slash them off. I'm like, why did you do that? They're like, because it's common factor. I'm like, that doesn't answer my question. Why did you still do it? They're like, because it's there, we can cancel it out. I'm like, but canceling means it's also common here. And then they realize that they spent up to grade 12 not really knowing what canceling means. Yep. But be my guest, please go ahead. You can factor it symbolically and then plug in the numbers inside of the bracket. Times 20, 27.1 or 21.7. Speed 21.7. Don't forget the square, please. Over R, which is 25.6. Is it? 5.6. That's it. So who's got an answer here? And by the way, what's the unit of this final answer? The unit, just the unit. Newtons, because it's force. It's force left. So it's something in Newton. Okay, so Josh got 1 point. 1.75. Do we have an answer to the problem? It's supposed to be 5.9. Who's got 5.9? 5.9? All right. And according to the sig fig situation, it is what? It is, well, this is 3 sig figs. This is 3 sig figs. Did they? Do we have 3 sig figs or 2 sig figs? All over? Huh. So I guess, so what's the only, probably, what's the only reason they actually what? They actually use 2 sig figs in this as a fine answer. What do you think? But even if they round, technically, they still should show 3 sig figs. It's probably because of what? 9.8. But we said then, what did we say at the beginning of the course, like almost the second day? Given constants are considered to be infinitely accurate, or infinitely precise, I should say. So the answer is 5 point. So if you do the calculation, what is it? 5.9 what? 48, so 5.95. Yep. Is this a big force? No, but it's a model airplane, and the mass is only 211 grams. So yeah, that kind of makes sense. By the way, get used to this way of doing what? Almost any centripetal motion problem, even in first year. This is really how it boils down to. Just write the FC formula and then go back to the diagram and tell me which one is positive, which one is negative. And the rest is just math. Okay, all right, let's look at the next problem. Okay. Okay, we have a 2 kilogram mass is spinning horizontally in a circle on a virtually what? Virtually? Good, no friction. All right. It completes, interesting. We have revolution information here. It completes 5 revolution or 5 full spins in as much time as 2 seconds. All right. The mass of the puck or whatever mass, there we go, is, sorry, the length of the puck, the length of the string, my bad, is 4 meters long. What's the magnitude of the tension that's capable of keeping the situation? Okay. First of all, what are the forces on the puck? But again, we're doing forces, so we still have to do an FBD. What forces are on the puck? Gravity, go ahead. Yep, go ahead, gravity. Tension. Sorry, I mean normal. And obviously, which way is tension acting on the puck? It's the only thing making sure it goes in a circle, so it has to pull in. I apologize for the dark surface. Next time I'm going to make it lighter. Tension. Okay. Do I really care about the FG and the FN? I don't care about their values, but do I care that they exist? Yes. Otherwise, there's no way this is going to keep, on the same level. It's either going to jump up or sink down if one of those beats the other. Okay. What's the equation for FC? FC equals what? FC equals mass V squared over R. Do I know the mass of the puck? Oh, just the mass of the thing. I do. It's how much? It's 2 kilos. Do I know the length of the string, which would act basically as the radius of the circle? Okay. Do I know the speed of the revolution? Right now, do I know it? Do I know the speed? Is it given to me? It's not. But am I given information from which to actually get it? Do you remember yesterday what equations connected V to the situation like this? The rectangle, keep going, but a rectangle was applied to a what now? To what kind of motion? A circle motion. Yep. So everyone, let's go to the next slide. Okay, FC equals m V squared over R. Okay, everyone here, let's do the V. What was V? Come on. Technically, it was, like Ahmed said, it was distance over time. But the distance now is a what? Is a circumference. Apparently, it's doing how many revolutions? 5. So 5 circumferences in how much time? 2 seconds. So really, V is 5 times 2 pi R divided by, okay, hold on. Should I make it capital T or small t? Again, we said that capital T is the time for how many revolutions? 1. But apparently, we're counting how many revolutions? 5, which means technically, is that 2 seconds the time for 1 revolution or for all of 5? So should this be capital T or just generic T, small t? Do you see, everyone? Do you see what I mean here? Capital T only measures how many periods? 1 period or 1 revolution. Apparently, we are basing everything on how many revolutions? 5. So technically, we're basing it off 5 T's, right? Like 5 full periods or 5 full T's. So you know what? Let's just make it small t, as if it's regular time. Okay? So equals 5 times 2 times pi times, what was the radius? 4? 4 meters, all right? Divided by 2 seconds. Well, this is going to, well, by the way, in a math course probably, or actually in first year physics, they would tell you, keep everything exact. Okay? That means don't you dare put 3.14 instead of pi. Keep pi as what? As just pi. By the way, how many people are used to that from grade 12 functions and radians and all that? Yes. Okay, so especially if they want answers to be exact, don't put decimal. So technically, if you think about it, this 2 does what to this 2? Great. So really, it just boils down to 5 times pi times 4, which is what? Which is 20. Sorry, yeah, 20, not 20, 20 pi in meters per second. Or, since we are physics people, we can approximate, no problem. 20 times 3.14, 62.8. And now I can feed that in there. Now, everyone, question. What's the only force from the FBD that's pointing horizontally towards the center of the circle? The only force. I know we have 3 forces, but 2 of them really have nothing to do with the what? With the direction of motion. They are just support forces. What are the 2 support forces we have? Fn and Fg. Either one of them pointing into the circle, which means, as far as I'm concerned, they have nothing to do with Fc. What's the only force that's actually giving existence to Fc? tension. And obviously, is it negative T or positive T? Come on, is it pointing out of the circle or into the circle? So technically, it's pointing positively. Whenever something points into the circle, sorry, into the center of the circle, that's positive. So really, it's just what? Oops, sorry. So it's just T equals, and now we can just plug in. What was the mass of the puck? 2, and then 62.8 squared, and I believe the radius was 4. Okay, who's got this? And by the way, what's the unit of this number? The final unit. Hmm? Newtons, because this T is not period. This T is what? This T is what? Tension, it's force. Good. Okay, who's got this? I mean, technically you should square, and then if you multiply by 2 and divide by 4, it's like you divided by 2, or basically got half. Yeah, well, 60 squared is 3600, right? So what did you get in 1900? Yeah, 1971. Okay. However, what's the sig big situation in this problem? All of the numbers are what? Or all of them 3? What would this one be? Very close to what? 1970. And you do not have to put scientific notation because this, we understand what 1970 means. Now, is this a small force or a big force? Come on. If I pull you right now with about 2,000 newtons, would you feel it? Of course you would. Actually, that's more than your weight. Remember, what's your weight? Your weight is your mass times 9.8. My weight, like 62 kilos, times 9.8. Yeah, I don't weigh more than 630 newtons. This is more than double my weight. This is more than double the gravity is pulling me down. How come this is big? Okay, everyone, question. Okay, who's got a stopwatch here or a cell phone or something? Yeah, go ahead. I want you just to tell me, okay, I'm going to clap. I'm going to clap. And let's see how short 2 seconds are. Everyone, let's see how short 2 seconds are. What was my time? Okay, I've got to clap again. Okay, so again, when I clap first, you start. When I clap second, you stop. I'm going to try to time 2 seconds. What was my time? 151. So one and a half. Okay, okay, let's do it again. Ready? All right. Okay, okay. 168, almost. Did you see how short that time was? That puck with a 4-meter radius. How long is 4 meters? All right. Imagine 8 of these. Why 8? Not 4. Why 8? Because it's the diameter, right? Everyone, the puck. Okay, how big is this classroom? 1, 2, 3, 4, 5. The puck went a circle this big. In how much time? Is that a fast puck? That's a very fast puck. How are you going to swirl a puck that fast? By giving it a small tension or a huge tension? Do you see what I mean here? Everyone, remember yesterday from? Can I spin this very fast? What do you think? I can. Why? How much is this distance, by the way? Roughly? Yeah, I would say maybe 9 centimeters, like 3 yards. Well, it's very easy to spin what? Can you imagine if this string was 4 meters long and I was still spinning it this fast? What does that mean? Small tension or a lot of tension? A lot of tension. Okay, so when you're trying to accomplish a huge distance over a very small time, you have got to be pulling things in. Yes. Sorry. Oh, okay. Within the string, every part of the string is being pulled what? In both directions. I'm talking about the puck. What's pulling the puck in? It's tension towards the center, which is acted on by the string. You're right. And that's why I always say, you can either give me the tension within the string or the tension on the puck. It's the same thing. Okay, it's exactly the same thing. So apparently, yeah, 2,000 newtons of force pulling it in makes sense.